Yeah, so today I'll talk about tropical solution type problems with new theorems in auctions by tropical geometry. Okay. So here's a recap from lecture 1. Last time we talked about tropical geometry as a way to translate, say, questions about auctions to questions about polynomials, and then take the Legendre transform, and we get to think about, regular subdivisions. Right? So the picture we saw from last time was, is everything okay in connection-wise?
Okay. Oh, sorry. Yes, everything is fine.
Everything's fine. Okay, perfect. Yeah, so like last time, say here we have a bidder, right, with one type of item, but could have multiple copies, and they bid on subsets, and then, here's the bid of agent 1 is U1. We take the concave hole, project it down. This gives the regular subdivision of this integers from 0 to 4 by U1. And this regular subdivision tells you everything you want to know about what's called the demand set of the agent at various prices. Okay. So the key advantage is that the tropical view is geometric. It's a lot of problems become easier to state. It's also easy to construct and analyze examples and counterexamples. And this is what we'll do today. We'll prove a couple of theorems using this technique. Okay. So last time we saw proof of the unimodalization theorem, which if I may remind you, it goes, we have a discrete auction, right, with valuations uj for the jth agent. We have n types of items, and the auctioneer could choose a price p, which is just a vector in Rn, where pi is the price of item I, right? So it's a pricing per item, right? And unimodularity theorem said that comparative equilibrium always exists at all points, right? If and only if the demand edges in the regular subdivision induced by each of these UJs are unimodular, right? And the proof of this, the key lemma was basically to geometrically translate what does it mean for comparative equilibrium to exist as a point. We translate that in terms of the regular subdivision, which is, C exists at a point A star if and only if A star belongs to the regular subdivision induced by the aggregated demand. Right?
Sorry, there was a question. Could you remind us what it means that a set of edges is unimodular?
A set of edges is unimodular if you take the you take a subset. So a set of edges in dimension n, right, is unimodular if you take a subset of n. You take that's non-singular, that's linearly independent. You take the determinant, and that determinant is always +1 or -1. Yeah. So it's in the sense of it's the same as a unimodular matrix, right? If I have a matrix A, right, that thing is unimodular if I take any square matrices subblock that I can take that has determinant, +1 -1 or 0 if it's not linearly independent. Okay. Great. Yeah. Okay. So geometrically in this picture here, what we mean is that, for example, here's delta U1, here's delta U2, right? How do I check if, so the set of edges of delta U1 are, I have the edge, this one, 0, 1, right? I have this edge, right, which is 1, 0, right? And I have this edge here, which is 1, 1, right? And then I have this edge, which is 1, 2, right? Those are the edges of my regular subdivision of delta U1. And similarly, I have, these are the edges of regular subdivision of delta U2. So I get 1, 0, 0, 1, and then I get one more, which is 1 -1, right? So altogether, these two guys give me 1, 2, 3, 4, 5 different edges. And this set of edges is not unimodular because if I pick this vector here, which is 1, 2, and this vector here, which is 1, 0, right? And I look at the determinant formed by the 2 by 2 matrix, 1, 2, 1, 0. If I compute that determinant, right, this is, this is -2, right? So that's not +1 or -1, so that's not unimodular. And geometrically, it means that if I form the parallelogram by this, apologize for the dog. I don't know if you can hear it. If I form the parallelogram formed by this edge 1, 2, and this edge 1, 0 here, then I get this parallelogram. And being not unimodular, it means that there is a integer point, well, at least one integer point that get trapped inside. Okay, so in this particular example, I have this integer point 1, 1. It lies strictly in the convex hull of inside the convex hull of this parallelogram, right? And that's a bad sign, right? Okay, great. Okay, great questions. Thank you. Okay, so last time we saw. Sorry, let me maybe I mop this up so it's not so cluttered. Yeah. So last time we saw that comparative equilibrium exists, right? If and only if the point that I'm interested in, the bundle I want to sell, A star, it lies as a marked point of the regular subdivision, right? So the example we should keep in mind, right, is is this picture here? That here's an example where comparative equilibrium fails at 1, 1. It's very easy to check, right? Here is the this is U1 evaluated at these points. So here I have a U1 that goes from Z2 to R. I have a U2 that goes from Z2 to R, right? These are the lifts, right? And so I lift this point up, take the concave hull, project it down. This is the subdivision I see, right? And now when in a auction with these two agents, right? This is the picture of the aggregated demand, right? So this is U, capital U from Z2 to R. That induced a regular subdivision of this bigger polytope formed by taking the Minkowski sum of these two. Right? Every cell in here is a Minkowski sum of some cell in here and some cell in here. Right? Right. And the point I'm interested in is this 1, 1. And unfortunately, this 1, 1 is not part of the subdivision. Right? It's strictly like below the subdivision. And so then I can immediately conclude there's no comparative equilibrium at this point. Right? There's no price P upon which agents are going to be happy at splitting this 1, 1 bundle. Okay. That's what we saw last time. Great. Yeah. Okay. I hope if you have any questions, please let me know. Okay. So that's fine, except the unimodularity theorem has a lot of proofs, right? And some of them don't need this geometric thinking at all. It was discovered, I think, first in 2003, right? It didn't need. It was just pure algebra then. Okay. So the question is. It's nice that we have cleaner proof of existing methods. Can tropical geometry solve new problems in economics? Right? Okay, so let's discuss this. May I have a volunteer to read out this example for me and the question as well? I'll just mute myself. If you could volunteer, then please read it out. That would be great. Thank you.
Okay, I can read it. So consider the cutlery auction of 3 items, a fork, a knife, and a spoon among 3 agents, fruit, spaghetti, and steak. Each is willing to pay at most $1 for their favorite combination and no other. For fruit, it is knife and spoon. For spaghetti, it is fork and spoon. And for steak, it is fork and knife. The question is, does a competitive equilibrium exist at 1, 1, 1 for the cutlery auction?
Wonderful. Thank you so much, Neil. Okay. Right. So we have an auction here, right? To be very clear, we have 3 agents, right? So when this part, each willing to pay at most $1 for a pair, but no other, right? What we mean is that for example, for fruit, right? So the valuation of fruit is going to be 0 for all A lies in 0, 1 cube, which I think of as subsets of these 3 things, except the point say fork, knife, and spoon, right? So this guy 1, knife, and spoon. So this is the first coordinate, this is the second coordinate, and the spoon is the third coordinate. So the only thing that fruit one is, oh, hang on, yeah. So yeah, I'll correct myself in one sec. But the only thing that fruit one is at the point knife and spoon 0, 1, 1. This has valuation 1. Okay. Okay, so I made a small mistake here, which is this will be 0 at all points except fruit would be okay with two points, right? He's okay with this one, and he's also okay with anything that contained the favorite item. So this would also be 1, right? So this is a common assumption, is that in a auction, if a point S is less than a point T, right, then V of S is less than or equal to V of T, right? So the idea is, if a bundle has more items than you wanted, you simply, if you wanted to, you buy the bigger bundle, and then you can just throw away the items that you don't want, right? So that's why the valuations for the bigger one is at least as big as a valuation of the subset. Okay. Just a normalization thing to make this function non-decreasing. Okay. So now the question is, so we have these 3 agents, right? The question is, does competitive equilibrium exist at 1, 1, 1? Okay, I would like to give the audience a minute, and perhaps you could let me know what you think. Wait, any thoughts on, I mean, for this problem, it might actually be easier not to think in terms of subdivision. I just drew it for visualization, but I think it is actually easier just not to think about it. Because my numbers are slightly funny here. I got messed up with the coordinates. So there should be one that's 1 here, and 0 here. Okay. Is there, so the question is, could you set a price for each of these items, right? Such that you can split them to these 3 agents, so that they're happy with their assignments.
So I'm not sure if I remember the definition precisely. So if we set the price of each item to 1/3 and assign all of them to the same agent, are all the agents happy?
Right, let's try. So if I put a price of 1/3, let's say I give it all to fruit, right? Okay. Now let's check, right? So if I have, let's check that fruit is happy, right? So fruit, for fruit, then definitely, right? So for fruit, they're happy, right? Because if the price is 1/3 and they value everything at 1, right? Then their profit is 1 minus 2/3, which is good, right? I think it is the maximum. Wait, hang on. Is this the maximum? So for fruit, sorry, let me compute this. Right. So oops. Sorry, it's like I lost my. Okay, so for fruit, I think there are only 2 points that we have to check, right? One is the utility for fruit at 0, 1, 1, right? That would be 1, right? Minus, so if fruit were to get the assignment of just 2 items instead, right? And they would get, if they just get their 2 favorite items, then they have to pay 2/3, and that's and so their utility for that bundle is 1/3. If they were to get all three items as you just assign them, then the utility would be 0, right? So then in this case, in fruit would be unhappy, right? Because they would have rather that you only give them the knife and the spoon, right? They don't want the fork, and you're charging them 1/3 for the fork, so they're unhappy, right? So this would be not a competitive equilibrium.
So basically we need to set the prices for 1/2, and then fruit doesn't care if we give them all the items or none.
Sorry, so your new thing is to set the price 1/2, 1/2, 0?
No, 1/2 for every item.
Yes. Yeah.
Oh no, that's too much. No, that doesn't work either.
Right. Yeah, I don't think that works either. Yeah. Right. So yeah. So you see. Thank you very much. I think that's wonderful. Yeah. So you see, if you try to play with this, right, you might say, okay, well maybe then maybe we should try. How about 1/3, 1/3, 0? So the fork is free, right? But if the fork is free, then fruit will be okay, but somebody else will be upset, right? Because because for example, say for spaghetti, who wanted a fork and a spoon, right? Then they got the empty set, which has utility for spaghetti of the empty set is 0, but under say this price where it's 0, 1/2, 1/2, then spaghetti would really want their favorite combination of 1, 1, 0, because that has if they were to get that, then the utility will be 1/2, which is strictly better than what they got, right? So yeah, so in sum, I mean, it's a bit without calculating by hand, it's relatively hard, but this problem has some symmetry. So after playing with this a while, we might conclude that well, this thing doesn't have competitive equilibrium at 1, 1, 1, right? Okay. Well, the answer is actually yes. You can get competitive equilibrium, but only if you do you generalize the pricing to nonlinear pricing. Okay. All right. So what's a graphical pricing? So a graphical pricing rule is I like to think about not price as a vector for a second, but I want to think about price as something more flexible, which is a function that assigns every subset of n a number. Okay, so that's That's like literally I can price different bundles at with different numbers, right? So if I do this in general, I need 2 to the n numbers. So that's a lot, right? So that's not so practical for computations. But instead of doing a linear look at the class of linear functions, I could look at the class of quadratics, right? And this has a really nice economic interpretation, right? Namely, the price of a bundle S is the sum of the individual price tag that you put for each item S, plus any discounts or marked up that you put for each pair ij, right? So pi, so price now as a function, it can really be represented as a tuple when n equals 3. Then I get a tuple that's p1, p2, p3. That's the prices of the first 3 items. And then I get p12, p13, p23. Those are the prices for the pairs. Okay? So I have n coordinates at first, and then I have n choose too many afterwards, right? Where this, we can think of it as a discount or some bonus, right? Depending on the sign. Right? So, so I like to, well, I claim that with the cutlery auction, then you can, under this pricing scheme, then you can find a price that achieves competitive equilibrium. So what would that be? Now let's also spend a minute. Yeah, while you think, I'll just recall the auction here. Great, we have a suggestion. Pi is a half, P12 is minus a half, P23, and P13 is 0. Okay, so let's try. So I have, let's try this P, a half, a half, a half, and then I think I had a minus a half, right? And 0, 0. And who are you, which agent are you assigning? I probably assume you're assigning to the one that wants the first pair, right? Probably, right? So, yeah. Could you say how you split this 1, 1, 1?
Yeah, I think giving it to the first, the one who wants the first two.
Right. So you put 1, 1 to this guy, 1, 1, 0 to this guy, and do you
1, 1, 1.
1, 1, 1. Okay, you assign 1, 1 to this guy. Okay. All right. Okay, so let's check that this works. 1, 1, and then minus a half. So that tells me, oh yeah, because I get all 1, 1, 1. Yeah, so I think this suffers from the same issue as before, right? Which is, I think this guy would have rather get 1, 1, 0, right? because if he got 110, then he would have paid a half, and then minus a half. So his value would have been a half. Whereas if you give him like this item that he doesn't need, but you're still charging him for it, then it's still he's going to be unhappy, right? Because then, right? So again, if I have this fruit, then v fruit at 110 is a half plus a half minus a half. Sorry, it's 1 minus this. This is how much he has to pay, right? So it's going to be a half. Whereas v fruit at 111 is going to be 1 minus a half plus a half plus a half minus a half, which would be 0. And so that suffers from the same issues. Two-third, each item costs 2/3, each pair discount 1/3, assign any agent all item and the other 2 agents no items. Okay, so let's try that one. Okay, so P is 2/3, 2/3, 2/3, and then I think the suggestion was 1/3 for each pair. Each guy get a pair discount of 1/3, so that would be minus 1/3, minus 1/3, minus 1/3. Okay, and I assigned it to any one guy. Let's say again assign it to fruit, right? So yeah, but this has, I think, the same issues, right? Because v fruit, if he were to get the 110, then he would have to pay, 1 minus 2/3 plus 2/3. Oh, I guess he would have to pay 1, so that would be 0. So he might be happy with empty as well. And then if I had, but I assigned him the 111. And I think that also works, right? Because if I assign him 111, then total amount of stuff he has to pay, I think adds up to 1. Perfect. Okay, yeah, perfect. So I think this works. There's no weird thing. Yeah. There's no weird stuff. Okay, great, wonderful, thank you. Indeed. So if we have quadratic pricing, then you can find a vector P such that and an assignment, right, such that competitive equilibrium exists. Thank you. I have another P prepared, right? So this P is this P is 0, 0, 0, 1, 1, 1, right? So I don't charge you for any of the items, except when you try to buy pairs, then I charge you, right? And in this case, I actually just assign 1 item to each agent. Everybody just cannot care less. Like everybody get utility 0. My own revenue is also is also 0, right? Because I'm giving the items for free. Nobody, I'm not giving a pair to anybody. But I could also, for the same price, I could also have a different assignment. So this is a price vector that comes with an assignment that has competitive equilibrium, right? This is the same price vector that comes with a different assignment that also has a competitive equilibrium, right? Namely, I'm going to assign first 2 things to one guy, and then the last thing to one of the other guys, and then nothing to the third guy, right? So in that case, as the seller, I get back $1 for being able to sell a pair, right? This guy is still happy. His utility for fork and knife at this price is 0, but it's the best thing he got. The fruit utility for the spoon is 0, but that's also the best thing they got. And the spaghetti utility for empty set is 0. But that's also the best thing. Okay. All right. So yeah, I guess in this mini example here, you can choose, even if you fix a price P that's competitive equilibrium, I want to point out that there are potentially several possible allocations that satisfy competitive equilibrium. I think one interesting problem we didn't manage to solve in the paper is to kind of do this revenue optimization for the seller. Okay. Well, we can talk about that later. Okay. So here is our main result in general. So evaluation. So we're specifically considering combinatorial auctions, right? So that is, every agent submits something that's, map subsets of N to R, right? And we're looking at the case where the agents are submitting graphical valuations, right? So a valuation is graphical if there exists a simple undirected graph G, right, on these n items, right, such that how much an agent value of bundle S is just, the agents themselves do a pair bonus or markup pricing, right? So how much the agent value of bundle S is just the sum of the agent's values for each of the item in S plus the agent's own value of how much they value like a pair ij over all ij in S. Okay, so in the previous example, I was drawing these little triangles here, right? This would be, for example, knife and fork. So this would be the graph that represent the valuation of steak, right? So for steak, each item is worth 0 individually, but the pair is worth 1. Okay, so with this graph now, we can infer, for example, that the value that stick has for, say, the set 111, right? This is going to be the sum of all the items in the set, which is 0, plus the sum of all edges in this graph. Well, this has value 0, this has value 0. So the sum of all edges in this graph, which will be 1. So this is an example. All the agents here have graphical valuations. Okay, great. Okay, so let's assume that the agents do graphical valuations, and my pricing vector is also a graphical valuation, right? Then the theorem is that as long as the graph that each agent has is a complete subgraph of n, right? So as long as so the agents don't necessarily have to bid on everything, right? They could put, minus infinity for bundles that they don't want, right? Except that their underlying graph has to, so the set of items that they want, it must form like a subcube, right? So the graph that they running this on must be a complete subgraph of n. As long as that's the case, then comparative equilibrium with graphical pricing is guaranteed to exist at any bundle in the cube, okay? For any auctions such that each agent's graphical valuation is supported on a complete subgraph. Okay, so I hope that's clear. So in my previous example, I do have complete subgraph, right? Because for example, my knife, my spaghetti is that agent has value 1 here, 0 here, 0 here, 0, 0, 0, right? So that is the agent's valuation is indeed, the graph that defined the agent's valuation is indeed a complete subgraph of the triangle, right? An example where it's not a complete subgraph is when I put values such as, I don't know, a negative infinity for this edge, for example, right? Because that's would mean, you never want this pair together, right? That this would, for example, something like this is not a complete subgraph, right? And then we have counterexamples that says you can cook up for big enough for at least 4 agents, and n is at least 4. You can cook up auctions where the valuations are not complete subgraph and comparative equilibrium failed at the point of your choice. So this is very similar to the unimodularity theorem in that it guarantees that as long as you sit inside a particular class of auctions where the constraints are put on what kind of valuations that the agents can submit, okay? As long as you sit inside this class, then you always get comparative equilibrium. Right? And this is rather easier to check, right? Checking whether something is a quadratic valuation. This is definitely in polynomial time. It's much easier to check compared to checking whether the edges are unimodular. It's also that the graphical pricing is also relatively easy to understand. Any questions? Yes, please.
I'm not sure I understand this complete underlying graph. So I mean, if you pick weights that are very, very, very negative, what?
Like -10 is okay, right? I think we just want to rule out negative infinity.
That's the only thing you're ruling out.
That's the only thing we're ruling out. Right? So negative 100 is fine, because then that's still, the graph is still supported. The only thing we rule out is negative infinity.
And no, there's also a question in the chat. What is the motivation for using graphs in practice?
Oh, so, what's the motivation of using graph in practice? Right. So first of all, it's very intuitive to, I mean, it's a, well, I have, yeah, first I have two answers. So one is that it's relatively easy to, you know, to form or to check that your valuations or your prices are graphical, right? It's an intuitive idea that when we sell, you take like discounts on pairs or something. But the other thing is that this class can model what's called, sorry, let me complete my sentence. So in economics, there's this concept we saw before of growth substitute that I mentioned a little bit, where when n equals 2, right, then, you know, you have this coffee and tea picture where where you want, basically you tend to want one but not the other, right? So these are, you know, for n equals 2, then these are these happen to be coincide with the class of submodular functions. In other words, having more of the, you know, like 1 1 having 1 1 is not as good as having coffee and tea. Is not as good as having coffee plus tea, right? It's not as good as that. The two items don't, they substitute of each other. Now the opposite of substitute is called complements, in which having the items together actually enhance their kind of their value to you, right? So the classical example is coffee and milk, or tea and milk, say, where having coffee alone is okay, milk alone is okay, but together they're better, right? So your subdivision will look like this, right? And in this particular case, for n equals 2, it coincides with supermodular bits, right? These are the complements, right? Okay, and now for quadratic bits, right? If you have, sorry, not quadratic, graphical. So if I have a valuation that's graphical, right, then that means if I think in terms of the subdivision, right, then if I restrict to any pair in my cube, right? If I restrict to any two-dimensional face in my cube, then I could choose this weights so that I can model both behavior, right? So that in my subdivision, I can have both this substitute situation and also this complementary situation, right? Okay, so right. So what that means is, well, you know, for example, in the unimodularity theorem, then you want to generally stay away from complements, right? Because complements have this 1 1 vector that it tends to, you know, if you have something that's complement, and then in another face of the cube you have something that's substitute, right? So then at one point you have let's say a 1 1 0 vector. At elsewhere you have, you know, 1 minus 1 0, right? So then that's in trouble, because if you take the you know, if you take the parallelogram formed by these two vectors, then you get an integer point get trapped inside, right? And so in, you know, I guess already in dimension 2, if one agent has a substitute and the other agent has a complement, then the set of edges that you get is not unimodular, right? Precisely because of these two vectors here, their determinant is 2. Okay, so that's bad. So unimodulated theorem then tells you that if you have such a, you know, some agents love these two things together, some agents really hate them together, then when you put them in an auction, competitive equilibrium can fail, right? Whereas if you have quadratic pricing, then that's okay, right? So as long as the agents, if you have quadratic pricing, you can allow the agents to model their preferences to be complement or substitute. And then as long as your pricing is quadratic, then, graphical, then this theorem says that you can find a price vector to get competitive equilibrium. So that's, it gives you more flexibility for the agents to participate in your auctions, which then hopefully is better for everyone. I hope I answered that. Okay, any other questions? Okay, great. All right. Okay, so yeah, so for example, in our theorem, right, indeed we check all the cutleries have quadratic pricing, and then that's an example where competitive equilibrium fail if you only use linear pricing, but it is fine if you have quadratic pricing, and this is this is implied by the theorem above. Okay. Yeah, so things to note. I was saying that this support thing condition, like you can't get rid of it. So if you have situations where agents, let's say they're happy with item A or B, or A or B or C, they're happy with A and B together, B and C together, but they never ever want A and C together. If they put that to be minus infinity, then you get into a lot of troubles, right? Then we can find a counterexample for competitive equilibrium when the number of items are large enough and the number of agents are large enough. Okay, but as long as you put like minus 50 or here, then that's okay. That's fine. Okay. Okay. That's one. The other one is we're mostly talking about auctions that are combinatorial. So that's you have one item of each type. So your valuations are stuck on the cube. If we want to generalize this to multi-unit generalizations, it's possible, but it's a little bit limited right now, right? So we have some theorems where you put a little bit of conditions on the graph, and then the generalization is fine. But otherwise, we're sort of restricted to the case where the bundle of interest, you either have no copy of the nth coordinate, or you have exactly r copies for the nth coordinate, right? So the vector that you're selling looks something like 0, 0, r, 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 0, r, for example, right? And so you need to have, so it's just simply like a multiple of this 0, 1 vector, right? And I should say that this is not true in general, that, if you have comparative equilibrium for the cube, you can immediately generalize this to this dilated cube. This is generally not true. So this took a little bit of sweat to prove as well. Okay, so our proof is constructive. Is an algorithm that tell you how to allocate and how to find the price, right? And it's there's some it's a little bit hard to outline, but underlying in it is a matching theorem. And the proof does not use modularity. We don't set up, there isn't any, or at least we haven't found a way to set it up as an integer program such that you can say, oh, under my condition, this matrix is unimodular and therefore I'm done. That's not the case. We don't think this proof can be reduced to just unimodularity in integer programming. Okay, so in particular, it just cannot be deduced from the unimodularity theorem. It's something completely different. Okay, okay, so I'll say a little bit about the proof. Well, I guess I don't have tons of time, but let me just give you a sketch of the key part of the proof. Okay, so if I have a graphical valuation U with a price vector W of the agent, right? So that means how the agent decide how much they value a bundle S is going to be, the sum of the values they put on each item plus the sum of the values they put on the edges. Then I want to think of this as the projection of a linear function on a polytope upstairs. Okay, so this is a function on the cube, but I really don't want to work with the cube. I want to work with the upstairs polytope, which in this case, the correct polytope is the correlation polytope. Okay, so this correlation polytope sits in a bigger dimension. So the cube sits in dimension n. Correlation polytope sits in dimension n plus n choose 2. Right, so the first n coordinates you imagine are for the items, right? And the next n choose 2 coordinates are for the edges. Okay, and the polytope I'm looking at upstairs, it's not the cube upstairs. It's the polytope obtained as indicator functions of a complete subgraphs of n, right? So here is a S. So for each set S downstairs in n, right? So for if n equals equal 4, say, I have 4 items I'm interested in, right? Then let's say a set S, which is, for example, the set 1, 2, 3, that will define this vertex, these set of vertices in a graph. And then if I take the complete subgraph of that, then I get this triangle here. And then that would, the indicator function of that graph, right, is, which we denote as, this is going to be, 1, 1, 1, 0. That's for the first 4 coordinate, right? That tells you which vertices you have. And then the next bunch tell you which edges you have. So I have 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Those are my next 6 coordinates. And then this graph will have edge 1, 2, 1, 3, 2, 3, and the rest is 0. Okay. So for each subset of n, then I get one such graph, right? So which each subset of n corresponds to one vertex of the cube. So I get one such graph, and then I lift it upstairs to get, to the n possible points upstairs, right, in a bigger dimension now. And if I take the convex hull, then that polytope is called the correlation polytope of the complete graph. Okay, so the set of the vertices of this correlation polytope is this set of points, A up arrow. And I really want to think of U as a result of taking a linear function on top of A up arrow. So I take a linear lift on A by this vector W, right? And then, and so that creates for me a linear lift of this polytope upstairs, right? And then I project down onto the first n coordinates, and what I'm going to see is the graphical valuation downstairs. Okay. So the whole point of working upstairs is that now comparative equilibrium, I can state it in terms of this upstairs polytopes, right? And I can state it purely in terms of regular subdivisions, and that's the key part. Right. So the key thing is that, well, one key thing is that because this lift is linear, right? Because how much I value a set is just the inner product of the weight vector W with this indicator indicator vector for the corresponding graph, right? So for example, in this guy, U of this set S is just going to be exactly equals to, right, U up arrow at AS, and this is just the inner product of AS with this weight vector W here, right? And this, if we expand it out, this is the same as the sum of all Wi in S plus the sum of all pairs Wij in S. Okay, so so downstairs is a very complicated, potentially complicated subdivision of the cube. That's because I just did the projection. Upstairs is just, I have a set of points, I lift it up linearly. So the regular subdivision of the guy upstairs is just trivial, right? It's just the correlation polytope itself. Okay. So now, if I have multiple agents, then I do this aggregation. So I get a much bigger lift upstairs. Okay. So this lift U now is going to live in, if I have J agents, then it's going to be living in, like, it's a map from the J dilated correlation polytope going to R, and it will create some complicated looking subdivision of that dilation. Okay. So yeah. Okay. So now comparative equilibrium, what does it mean now? It's that well, I guess actually I do have it in this slide. Comparative equilibrium at A star, which is a point in the cube, that exists if and only if at least one point in this fiber of A star is a marked point in this regular subdivision of delta U. Okay. So let me, so this fiber A star, pi inverse A star. So pi is just the projection from, R n plus n choose 2 projecting down to Rn, and it's just keeping keep the first n coordinates. Okay. Okay. So so pi inverse of A star is any lattice point upstairs where the first n coordinate is equals to A star. So the typical example, let's think of A star as the 1, 1, 1 vector. Then which we think of it as you know, that I have one item of each type. Okay. Then upstairs, what I'm looking at is any vector such that well, you know, if upstairs, if I have integer vector, it corresponds to graph with weights, right? So any graph such that the vertex coordinates are 1, right? But the edges could have arbitrary weights. So the edges, for example, here could have weights 2, you know, -1, 0, for example. That is a valid vector upstairs inside this space here, right? R to this dimension. That vector belongs to this fiber here, right? Because its projection onto the first n coordinates is my targeted point 1, 1, 1. Okay, so I have infinitely many such vectors, right? It's a particular, I get a whole subspace of such guys, and I just need that subspace intersecting with the regular subdivision to be non-empty, right? And why is that? Because if I have a point, a marked point, a point that's lifted inside the subdivision, then when I project it down, at that point I would see it get projected down to become A star. Right, so that means that there's a way to decompose this guy upstairs, this one point inside my subdivision upstairs. So there's a way to decompose it such that it corresponds to, you know, it's such that if I just look at the first n coordinate, it corresponds to splitting splitting these set of items. Yeah, and the decomposition tells me how do I allocate for the agents. Sorry, it's yeah, I really wanted to draw a picture. The only issue is that already when n is equal to 2, then this thing is well, n equals 2 is really a bit too small, and then anything n equals 3, this dimension is so large that it's just kind of impossible to see, right? But the gist of the problem is that I still get a condition on comparative equilibrium stated in terms of polytopes, but now I can see exactly why there's more flexibility for graphical pricing, right? So for linear pricing, I need exactly one point to be lifted, but for graphical pricing, I just need any points in this subspace to be lifted, right? It's a low-dimensional subspace, but any point that get lifted in this subspace would do, right? It doesn't have to be one particular point. And so because I have a lot more choices, then this is sort of roughly why, sort of intuitively why graphical pricing is more powerful. Sorry.
Ngoc, we have a question in the chat. Are all points in pi inverse A star legal partitions?
Are all of them legal partitions? They would only be legal if they lie inside the convex hull, right? Okay, so in the same way that I have, you know, if I have points that are, I don't know, 200, like, yeah, if I have points that are too far out, so any points in the convex hull, it means that I have a, you know, if I write up the linear program, then I have a fractional solution, right? And so that's legal, right? But the only thing is I need basically an integer partition of this guy. And so that is when I need it to be a marked point, right? So that's the marked point tell me I have an integer solution, right? But lying in the convex hull alone, it's a legal solution, of which I agree with you, they're not infinitely many points, right? Because this is a finite polytope. I'm intersecting with a low-dimensional subspace. I get, you know, some polytope, right? Of which some compact polytope, of which there are finitely many integer points, right? So those are the set of integer points that we look at, right? But it tends to be more than one, right?
So the question is the pi minus 1. It might be not a click, it might be a tree, something like that. So why it must be, so if you say, okay, at least one point in this, but this point might be a tree, so it cannot be a feasible allocation, right?
Yeah, so there could be tons of points that are not, you know, valid allocations, but I just need one point that's valid, right? So does that answer your question?
Okay, maybe we can talk later.
Yeah, okay. Yeah, maybe we can talk later, right? But yeah. Yeah, great. Okay. Yeah, question.
Sorry, just another question from the chat. Is there a generalization to the setting where valuations are described by hypergraphs with hyperedges of size at most k and prices involve subsets of size at most k?
Yes, there's a direct generalization where you replace the correlation polytope with the corresponding object, right? Which is you get indicators of this, well, let's say I look at 3 hypergraphs, right? Then I get indicators of something in dimension of n plus n choose 2 plus n choose 3, right? Where the set S now is going to correspond to, like a colored in simplex like this, right? And then, right, so this is why I think this is why I guess I keep saying quadratic, because you can expand this to cubic and, et cetera, polynomial power worth of pricing and valuations. What we haven't, I think this lemma would 100% hold, but what we haven't checked, which is like the bulk of the paper, is whether the theorem holds in general, right? Whether I can say that if I have hypergraph valuation of order R, right, for R bigger than or equals to 2, then, and the pricing is of the same sort, then I always get competitive equilibrium no matter what, right? So that's a bit unclear to us that that's true, because when we're doing this stuff, like we use some properties of the correlation polytopes that we haven't really understood what's happening, what's the analog upstairs. Yeah. One thing I know for sure that's true is if you expand this all the way to, n plus n choose 2 plus da 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 plus n choose R, R going from up to, all the way to n choose n itself, right? So this is just saying now my pricing is going to be, I put a little increment change for every subset of all sizes, right? So then for sure in this case, you can get competitive equilibrium. That's just, that's because when you lift it up to this height, then that polytope upstairs is effectively a simplex in a very, very high dimension. And because everything is a simplex, then you're good. Yeah. So somewhere buried in here also, I believe, is like something about, approximating a polytope with with a simplex as projections of simplices. And it's probably there should be connection with there should be a trade-off in computational complexity as well, right? So if you can only represent a class that's polynomial, then I think you have to fail comparative equilibrium at some point. For us, it fails if the support is not on a complete subgraph. Yeah. And I suspect something similar like that is true for hypergraphs. Okay, any questions? More questions? Thank you for the questions. That's great. Okay. Right. So the second lemma. So this lemma said, how do I get competitive equilibrium at a point? And my theorem, I want to basically get competitive equilibrium. Yes. So this is how do I get competitive at a point for a particular auction, right? Because my condition said that so and so, some set is a set of marked points in the aggregated valuation, right? This second lemma is more in the spirit of doesn't matter what auction you pick. There's a condition that you can check, right? Doesn't matter what use you pick. There's a condition that if you satisfy, then doesn't matter what auction you pick, you for sure will get competitive equilibrium at A, right? So the lemma specifically said competitive, CE with graphical pricing exists at a particular A star for any auctions with graphical valuations, if and only if for any pair of, or for any tuple of J faces of the correlation polytope, there exists at least one point in this fiber such that if this point A prime lies in the convex hull, right, of the Minkowski sum of these faces, then it must lie. It must be able to be written as a Minkowski sum of the vertices of these faces. Okay, so right, so there's some existent stuff to, this lemma, I think, is just a little hard to digest. I don't think it's very easy to prove it immediately, but the key point is that it's translate the economics problem of, how can I guarantee that doesn't matter what auction, I always get competitive equilibrium, right? That's that part, that's the economics part. We translated it to a problem purely about the correlation polytope, right? Namely, if you have J copies of this correlation polytope, you are free to pick any, for each of your copy, you're free to pick a face, okay? And now you form the Minkowski sum of that face, okay? So of those faces, that gives you some polytope, right? And I need to check that, and then I have this set here, this fiber set. I have to find a guy in the fiber set such that whenever that guy is lie inside your convex hull, then it has to be an integer point, right? It has to be, it has to lie as part of the Minkowski sum of the vertices, right? So it has to be lifted, basically, right? So it's purely a question about there is a particular property of J copies of the correlation polytope that I need to check that has to be true. Okay. Okay. So then the bulk of our proof is to check that this is true. Okay. Great. Okay. So there's maybe I should wrap up. I actually have I wanted to talk about the second problem, but I definitely don't have time for that. But thank you very much for the interest on this one. So more details on this. So generally, this falls into, there's a literature of people looking at graphical biasing and valuations. I believe in this paper by Canagan, Ostakla, and Parillo, they also do the hyperfield, the hypergraph case. So they mention it, but they don't prove competitive equilibrium. The analysis of hypergraph is, at least right now, is quite taxing. I learned a lot from this paper by Rathgarden and Tagam Cohen. This is the paper called Why Prices Need Algorithms. And it's a kind of a CS tech on auctions that I really like. So this paper was brought to my attention by Professor Rakesh Vora, who's an economist at Penn, and he asked whether tropical geometry could help in analyzing these more general pricing rules. So yeah, our paper is here. So what's opening is pricing with triples, or in general, like hypergraphs, and then the other thing is quadratic pricing with non-complete graphs. So we have we have a family examples for at least 4 agents and at least 4 items, but that's that's not to say that if you have non-complete graph, then competitive equilibrium would always fail. It's that you can construct like a bad case, and it's not clear to me that how often is this bad case, and whether it's worth worrying about is another matter. Okay, great. Well, thank you very much for your time. I'll just stop here. Yeah.